Okay, good afternoon. So the plan for today is to talk about trig integrals and trig substitution 7.2 and 7.3. Note that supplement 1, which mostly just talked about material that's due this coming Sunday, was posted this past weekend. So that's up and available for you. And also note that the Unit 1 exam is coming up in a couple weeks. That'll be on chapters 6 and 7. The week that it will be during is set in stone, so to speak. But if we're say running a little behind or something, and this goes for any of the exams, I would adjust the material on the exam before I would adjust the date of the exam. So for this exam or a future exam, if we're say running a little behind schedule for some reason, if we get a cancellation, the material on the exam would change, but the dates would stay the same. The exam does use Examity. So this week and the next day or so, I'll post an Examity practice exam and a little more information in general about that. So the Examity practice exam won't be for credit. It won't be a long exam or anything like that. It'll be a couple of Calc 2 questions, but the only purpose for the Examity practice exam is really for you to go through the Examity process once, for you to kind of go on, log on to Examity, get the session started, log on to WebAssign, go through the motions to get the exam on WebAssign started up. And then you can, do those couple of problems again, like, just a couple of problems in there to give you something to, kind of do on the exam. You can work through them. It doesn't matter if you get them right or not. It doesn't matter what score you get. And then you can close out the WebAssign exam, close the Examity session. And just for you to be able to kind of practice doing all of that once before the actual exam. So look for details on that posted later this week. And then, you'll have gone through it once and you'll kind of know what to expect for the Unit 1 exam, the actual exam that counts, coming up in a couple of weeks. So are there any questions on anything before we get started?
I just had a quick one about the exam.
Yeah, definitely.
Do you allow like formula sheets or like a scrap sheet of paper that we can use
Yeah,
that has like notes on it?
yeah. So what I'll allow is like one, standard size sheet, 8.5 by 11-ish, front and back. You can write formulas, notes, anything like that that you want on, one standard size sheet of paper, front and back. So I don't give out a formula sheet, but any, formulas or anything that you want to write on that sheet, you can use, you can write on there and then use during the exam. Yep. So you can use
Okay.
a sheet like that. You can use scratch paper that has to be blank at the start of the exam, pen, pencil. You can use a calculator as long as it just has to be only a calculator. So you can't use a phone, a tablet, Desmos or something like that. You have to have a calculator that is only a calculator that you can use. Strictly speaking, you should be able to get through this course, almost all of the sections without, a calculator. But sometimes it can make some of the tedious bits a little easier. So yeah, you can use the calculator as well. I think that covers everything. Yeah.
Okay. Thank you.
Yeah. Any other questions on the exam? Anything we talked about last time, the homework, anything like that?
I've done some exams through Examity. I've done the live proctored, and I think the automated. You said this was automated. So if we're allowed the scrap sheet, so we just sort of like show like our formula sheet. Like, should we hold it up for like a long time, or is there
No,
no
you can have
requirement
whatever you
to?
want on it. So
Okay.
so yeah, that's fine. I mean, it'll be kind of obvious from the camera if there's a whole bunch of sheets or something like that when you do the what do they call it, the environment scan. But yeah, so yeah, you don't have to worry about holding it up or anything like that.
Okay. Thank you.
Yeah, that's one of the reasons I say you can just have whatever on it, because I don't want to sit here and try to decide what counts as a formula and what what doesn't count as a formula. Like yeah, so anything, front and back of one piece of paper. Any other questions? Okay, so the quote of the day is a quote attributed to Albert Einstein. You know, when you tend to be famous and smart like Einstein was, people randomly attribute a bunch of stuff to you. So I'm not 100% sure if he actually ever said this quote or wrote it, or if he was the one who came up with it. But I've also heard it said by Warren Buffett, you know, kind of quoting Albert Einstein, where he says, compound interest is the most powerful force in the universe. And I think in terms of finance, that's, you know, certainly a true idea that if you start investing early, that's going to pay off a lot more at, say, retirement age than if you start investing later, because you can capture those years of compounding, that compound interest, that exponential growth. But as a more general idea, positive feedback in the sense that some phenomena can self-reinforce, they can build on each other, can be extremely powerful. So if you choose to, you know, learn things that are more foundational and that have a longer time constant, then you can build on those things, and piece of information 1 might help you learn piece of information 2 more easily, and those 2 might help you learn 3 more easily, and so on. But also note that, you know, power can cut both ways. These can also, you know, this idea of positive feedback isn't always a positive thing. The idea of a self-reinforcing phenomenon can lead to a downward spiral as well. But particularly when we're looking at, you know, say chapter 7, where we have material that's really strongly building on each other, right? Really building on the chapter 5 material, and then saying, okay, if we understand the chapter 5 material, we can use some of that that knowledge from, you know, some basic integration techniques to either check those first before we go to more complicated ones, or to really leverage that information in something like, say, a trig substitution or solving a trig integral. We're starting to get to the point where material is building on each other. That means if you understand the foundational material very well, say it's the substitution rule, then this material will come much more easily. But on the flip side, if you don't understand the substitution rule from chapter 5, this material is going to be quite difficult. So make sure you're solid with those foundations, and that'll make this material much more, I don't want to say easy. That's a little bit of an incorrect statement, but it'll make it much more manageable. Okay, so let's review a couple of trig identities before we get to trig integrals. So our first trig identity, of course, is the Pythagorean identity. Sine squared x plus cos squared x is 1. Definitely don't want to forget about that one. And we have other identities related to that. So for instance, sine squared equals 1 minus cos squared, or cos squared is 1 minus sine squared, directly related to it. Or if we were to say, for instance, divide by cos squared of x, we'd get, well, sine over cosine is tangent, so we get 1 plus tan squared x is 1 over cos squared x is secant squared x. So, right, Pythagorean identity in its basic form, but we also want to have in the back of our mind all of these kind of permutations of this main identity. And I would say the other ones, well, at least kind of the next basic one to know is the double angle identities, from which you can pretty easily find the half angle identities. So the double angle identities cos of 2x and sine of 2x. Sine of 2x is 2 sine x cos x. And cos of 2x is cos squared minus sine squared. Anytime we have an identity or a formula with a minus in it, it's easy to forget which order things go and to get off by a negative. But if we look at, say, plugging in x equals 0, cos of 0 on the left should be 1, cos squared of 0 on the right is 1, sine squared of 0 is 0. So if I had these backwards, if I mistakenly thought it was sine squared minus cos squared, I would be claiming that for x equals 0, 1 equals negative 1. Clearly, that's not right. So for any of these where I'm not, 100% sure about an ordering or something like that, I can always pick a particular input that's easy to evaluate and just kind of check, that of course doesn't guarantee that it's right. But if I have the general right pattern, that's going to be usually a pretty good check. And then we have a couple more identities that we could get from the combination of these two. Cos squared x is 1/2 times 1 plus cos of 2x, and sine squared x is 1/2 times 1 minus cos of 2x. And again, if I forget which one has the plus and which one has the minus, just plug in x equals 0. I see on the left I have 1. On the right I have 1 plus 1 over 2 as 1, so that checks out. And same with the second one. Plug in 0. On the left I have 0. Plug in x equals 0. The left side I get 0. The right side I get 1 minus 1, 0. So that checks out as well. Okay, so how can I leverage these identities as well as some basic substitution to solve trig integrals? Now, when I say trig integrals as opposed to trig substitutions, I mean integrals that have as the integrand sines or cosines or perhaps other trig functions. So for trig integrals, I kind of see explicitly in the integrand a trig function. And we're going to focus really on integrands that have sines and cosines multiplied together to some powers. Now, if I look at this first example, integral of sine squared x times cos x dx, I might try to, look for some kind of, could I turn the sine squared into a cos squared somehow and get a bunch of cosines? But even if I got something like, say, a cosine cubed of x, I don't really know how to integrate that directly, right? So even if I did get to something like cos cubed x dx, I'm not really sure where to go from here. But before I even do anything that complicated, again, I always want to look for something simple first. So I may think all the way back to chapter 5 before I try to do something complicated with trig identities or anything like that. And I might ask myself, is there a substitution I could do here?
Cos x into sin x can be written as sin 2x upon 2, maybe.
I'm not sure if I caught all of that, but I think the idea was if you use u equals sine of x, right?
Yeah,
Then
sin of x upon 2.
sine of x over 2. Yeah.
Yes.
Yeah, so a lot of times you can use a different a lot of times I guess you can use a constant multiple. I would probably just start with sine of x. But if you use sine of x over 2, that probably could end up working out as well. My du here is going to be cos of x dx. And now I see that this bit turns into u squared. And nicely enough, that cos of x dx all is just du. So just with a basic u substitution, this one ends up working out just fine. The thing that I had to notice here was that I had a sine of x all squared, and the derivative of the inside was also in my integrand. So this is 1/3 u cubed plus c. And now because I was asked the question in x and I have an answer in u, I really should move back to x. So 1/3 sine cubed x plus c. So this is one of my tricks for trig integrals. Just look for a basic substitution. I didn't quite leave myself enough room between each of these, but if I come down here, if I have something that's a little more complicated, I still have products of sines and cosines, but I have a higher number of powers. So here I have 4 factors of sine and 3 of cosine. Now, if I want to do something like up here, I could think of doing, taking u equals cosine of x or u equals sine of x. I see that my du is not going to work quite so nicely, right? So I don't just have a cos x dx or a sine x dx where it would be obvious what the du is. But if I start with something similar, say u equals sine x, du equals cos x dx, I can realize that this integrand, and OneNote loves correcting my 4s to 9s. This integrand has a sine to the 4th of x. That works nicely with u. I have a cos cubed of x dx. Well, I can break off one of those cosines. Instead of cos cubed of x, I'm going to use cos squared x cos x dx. So just breaking one of those cosines off so that I have a du. So this bit's good, this bit's good. I do have a bit of a problem though. I have this extra cos squared x, right?
1 minus sine square x.
Exactly, yeah. So cos squared is 1 minus sine squared x. Or in other words, 1 minus u squared. So I can rewrite this as integral of u to the 4th times 1 minus u squared du. And here I want to multiply out. It might be tempting to try to do some kind of crazy integration technique here or something, but easiest is just to multiply out, I think. And then plug back in my u's. So if I think about this pattern, what I realize is that any even power of sine or cosine, I can switch to the other one. And if I have an odd power somewhere, I can pull off one of those powers to be my du. And then what's left over is an even power that I can switch back and forth. So if I have the integral of some sines times some cosines, where overall I have an odd power. So in other words, if I have 2 plus 1, I have a total of 3 factors of combined between sines and cosines. or I have 3 plus 4, I have 7 factors combined between sines and cosines. I take the odd one out, literally, the one with the odd power, and I split off one of its factors to be my du. That leaves me with an even number of factors of that one, and also an even number of factors of the other one. Right? If I have two numbers added together are odd, one has to be even, one has to be odd. So whichever one is odd, split off one of those, leaving me with an even. The other sine or cosine has an even number of factors, and then I can switch one to the other however that's needed to make my u's and du's work out. So if I have an odd total number of powers, then this strategy works. I can split off one factor from the odd to take care of my du. What if I have an even total number of powers, or in this case, just integral of sine squared of x dx? I guess I could switch this to a 1 minus cos squared x dx, but that doesn't help at all. I can't use this same kind of pattern up here. I can't switch this into a sine x times sine x dx, because I would want du to be sine x dx, but I'd also want u to be sine x. Those aren't going to work out. And it's not easy for me to switch between sine and cosine in the first power or in an odd power. So I can't switch that.
Can we write sine square x as 2 sine x by 2 cos
Yep.
x by 2?
We're getting there.
Okay.
We're getting there. Yep. So if I tried something like this, the reason it doesn't work is if I could somehow magically switch this to cos x, this would work just fine. But the issue is that's not easy to do in a first power or a third power or a fifth power. Super easy to do in, say, a second power. Even a fourth power, if this was like sine to the fourth of x, I can think of that as sine squared all squared, and then do a 1 minus cos squared all squared. Yeah, but exactly, that's the problem here. So we can't really do this without making a huge mess and making the problem even worse. But exactly, we have some identities that are going to help us out. And in particular, this one here. So what's the magic of this identity? It takes a square, sine squared of x, and converts it into something where all that I have is a cosine to the first of x. The kind of cost of doing that is that I have cosine of something complicated, a little more complicated than just x. So I just have to be careful with my substitution, making all of the chain rules work out right. But exactly, we'd want to use this identity. So I try something simple, or I at least consider something simple. I see that that's not going to work. Move to the next more complicated thing. What I don't want to do with these problems when I just have a random integral plopped in front of me, when I don't know that I'm in section 7.2 and I'm going to need to do something like this. I don't want to jump to the middle of the complication scale, right? We're covering these techniques kind of in increasing order of complexity and difficulty. So I always want to start by thinking, can I do something simple? Can I make an algebraic simplification? Can I do a basic substitution? That's not going to work here. Be nice if it did, but it doesn't. Oh, 2x. And something important to note here, we're not doing a substitution. Just like with integration by parts, it wasn't a substitution. It was just kind of rewriting things, right? It was just applying a formula. Same thing here. Sine squared x is this big thing here, 1/2 times 1 minus cos of 2x. I didn't change variables at all. I didn't, come up with a u substitution. I just rewrote sine squared x as this thing, the same way that I might write, I don't know, x over x squared is 1 over x or something, provided that I'm not like dividing by 0 or some crazy thing like that. Essentially what I did here is equivalent to an algebraic simplification, but just using a trig identity. And I see here that I can do integral of 1 dx is just x minus what differentiates the cos of 2x. That's going to be something like a sine of 2x. If I differentiate this, negative sine of 2x differentiates the negative cos of 2x times 2. So I need another 1/2 in there to fix that. Or if you wanted for this step, you could do a use substitution. But I think for this one, the kind of guess and check method is maybe a little quicker. So that's our trig integrals. Any questions on these? So for integrals of sines and cosines multiplied together, if we have an odd total number of powers, we look for an approach like this, where we pick off the odd one out to be the du, and then the other trig function more or less is going to be the u, and we make everything else look like the other trig function, the one with the initial even power. If we have an even number of total powers, we go for something along these lines. In the supplement, we'll do some more examples of this, drill some more problems and so on. But to introduce the idea, I think this is a good assortment of a few examples showing just the general strategies. So moving on to 7.3, everybody's favorite, trig substitutions. So the basic idea of trig substitutions is if I have an integral in x, or my integrand is in x, normally with a substitution, if my integrand is in x, I set a variable, say u, equals some function of x. Trig substitutions work a little bit differently in that they kind of take the opposite approach. They kind of look at things flipped around. If I have an integral in x, I want to use a substitution where x is related to, say, a new variable theta through something like this, through a trig relationship like this. Let me shuffle my papers over here for a second. And the canonical example of this is something like integral of square root of a squared minus x squared dx. So an integral related to a function that kind of looks like the top half of a circle with radius a. Now, if I look at this, if I think through my basic techniques, do I just know what the antiderivative is? Probably not. Is there anything algebraic I can do here? I might be really tempted to kind of, quote, distribute this power across the subtraction, but parentheses, exponents, multiplication, division, addition, subtraction. Distributive property takes me one line down on PEMDAS, not two. So it might be really tempting to try to do this, but that doesn't work. So be careful that when you're looking at these integrands and you're looking for algebraic simplifications, that you don't get sloppy with the algebra. Super easy to get sloppy with the algebra when there's so much calculus going on. So we don't want to do something like that. I mean, that would certainly make the integral easy to do, but we'd have the wrong answer. Do I see a substitution I could use a simple substitution? Not really. The only thing I could even think of substituting might be something like x squared or a squared minus x squared, and I don't have a 2x dx to help with that. I don't see any integration by parts really working here. Differentiating the square root doesn't make it a whole lot nicer. Integrating it is the same problem we're trying to do here. I also don't see any sines or cosines in here, so trig integrals probably isn't the way to go here. So we've got to come up with a new method to approach a problem like this. And the new method is to use the substitution, like x equals a times sine theta. So we're coming up with a new variable, theta, that we're going to rephrase the problem in, similar to how with a normal substitution, we come up with a new variable u, in which we're going to rephrase the problem. But instead of writing theta equals some function of x, we're thinking of things the other way. We're writing x equals some function of theta. Now, what's my goal here? Well, my goal here is that x equals a sine theta, that feels very, circular in a sense, right? It feels very closely tied to a circle. And I know that this integrand is related to a circle. Or in other words, if I swap in, geez, my writing is atrocious today for some reason. If I swap in a sine theta for x, I get a squared sine squared theta. And a squared factors out of both terms, comes out of the square root as an a. 1 minus sine squared theta is cos squared theta. And square root of cos squared theta is cos theta. Let's assume we're operating in an area where cos theta is positive, so the square root of cos squared theta is just cos theta, and we don't have to worry about whether it's absolute value of cos theta or something like that. This is a heck of a lot easier to integrate. It's a heck of a lot, well, let me say it's a heck of a lot nicer of an integrand than this square root up here. Now, it can be very tempting. This is another place that it's very, very easy to go wrong. You do all of this work, you're like, all right, awesome. What did I miss here? Super easy mistake to make. What did I miss in that arrow step, in that step I just did?
The d theta.
Yeah, so I just claimed essentially that dx equals d theta, but that's not actually the case. So super, super important step, dx equals, I mean, I can't tell you how many times I've done this, over doing so many of these problems. It's so easy to miss this because you get all excited. You're like, oh yes, it worked out just right. And you're going to the next step and then it's ends up being wrong. Dx is a times cos theta d theta. So actually I have a squared cos squared theta d theta. Right. This dx picks up an a cos theta. And then my original integrand, the square root of a squared minus x squared, turns into a cos theta. So this gives me a squared integral. Now this I recognize. This is just a trig integral. This is similar to my integral of sine squared x. It's an integral of sines and cosines with an even number of total powers. I'm going to look back up to my trig identities, and I want to use my identity for cos squared x, 1/2 times 1 plus cos 2x. Well, and my variable is theta. So here, my a squared just as a constant, it popped in front of the integral. And then my cos squared theta, by a trig identity, just by what amounts to the equivalent of an algebraic simplification. Or maybe in this case, an algebraic complication. It looks a lot more complicated. It just expanded to this 1/2 1 plus cos 2 theta. And then my d theta came down. I have to be so careful with the bookkeeping, so to speak, and some of these like integration by parts and trig substitutions, just to make sure that all of these little nuances don't get skipped, that I don't just mistakenly turn dx into d theta and forget about this extra bit here, or that, just being cognizant of the fact that I'm just applying an identity here. I'm not actually doing another substitution. Everything just stays in terms of theta. So this 1/2 can come out. When I integrate, I get theta, because I'm in theta now. And as an aside, we're always in these cases thinking of theta up here in radians. Usually we say we're thinking of radians anyway when we're in calc or even, later parts of trig. But usually that's just like, oh, we're going to use radians because, we like seeing pies pop up or something. I don't know. Here it's actually crucial, right? Because when I want to integrate 1 d theta, well, if theta is not in radians, that's not going to work too well, right? I'm going to have, 30 degrees plus number. Those aren't the same units that I'm trying to add together. I absolutely better have theta in radians here to do these computations, because my thetas are coming outside of the trig functions. When the theta is inside the trig functions, it's like, if you have degrees in there, the trig function kind of kills the degrees and turns it into a number anyway. But when you have a quote angle, in a sense, outside of the trig function being added to other numbers, it had better be in radians. Otherwise, we have a big units issue. Okay, so the 1/2 came out. The integral 1 d theta turned into a theta. The integral cos of 2 theta, that's going to integrate to something like sine of 2 theta. If I differentiate the sine, I get cos of 2 theta times 2, so I need a 1/2 to fix that, plus a constant c. And I could leave this in this form. And I think probably, this is probably one of the few exceptions where leaving it in this form isn't, really terrible. But let's go a little bit further with this one. Okay, if x equals a sine theta, let me do this maybe in a different color. So at this point, we've finished the calculus. We've got an answer for the integral. We probably could leave it in this form. Well, let's try to get back to the original variable x. So x equals a sine theta, or this means sine theta is x over a. I can draw a triangle that represents this relationship. Let's look at a right triangle with angle theta here. And I know that sine is the opposite over hypotenuse. So the opposite side is going to be x. The hypotenuse will be a. And what is my base here going to be? Well, I have a squared, let's call this just b, equals b squared plus x squared. B equals square root of a squared minus x squared. Hey, that's right where that came from. Okay, so sine theta is x over a, so theta is inverse sine x over a, or arc sine x over a. I'm not going to write a sine because we already have constant a's floating around, and that might get a little confusing. So I'll write sine inverse x over a, meaning the arc sine of x over a. So what's sine 2 theta is 2 sine theta cos theta. So I'm going to write this a little bit like a mutant kind of statement here. We'll have one step where we have information in both x's and thetas. I don't know, maybe that's a little bit of bad form, but we know we're eventually working my way down to x's. I see that my 2 and my 1/2 go away. So really I'm interested in what's sine theta times cos theta. Well, sine theta is x over a. That's not too bad. What is cos theta? Well, cos theta I know is adjacent over hypotenuse in that same triangle up here, in this kind of reference triangle. That's the same theta that's in that cosine theta. So it's what? Adjacent divided by hypotenuse. I mean, it's not the prettiest answer in the world, but sine theta times cos theta is just the product of these. And maybe we can make things maybe a little nicer looking by distributing the a squared or something, or but I mean, this is pretty much it's not going to turn into, you know, just something super nice. This is what it's going to be. So again, you know, if we leave the answer in theta or switch it into x, you know, maybe there's a little bit of an argument for switching it into x because that's the original variable that was asked for. But maybe there's also an argument for leaving it in theta because it tends to be the case that when I switch back into x, things get pretty messy. Now, there are some of these, like say integral of 1 over root a squared minus x squared, that actually work out, you know, pretty nicely. They're not so bad. So then switching them back into x makes a lot more sense because the end result is going to be quite nice. It's just going to be a single function of x. Any questions so far? So a couple of big ideas here is, one, if I recognize something that looks like a trig relationship, this root a squared minus x squared, that really has like a trig feel to it, right? A circular feel to it. I'm going to consider a trig substitution. I'm looking for a substitution where after I do Pythagorean identity and simplify everything down, I'm going to come up with something that is easier to work with. That does take a little bit of kind of strategic thinking, right? A little bit of thinking a couple of steps ahead. What is this going to look like, right? If I plug something like a sine in here, 1 minus sine squared, I can mess with the constants to make it look like 1 minus sine squared. That's going to be a cos squared. I can square root the cos squared. That seems like a good plan. It might turn out that that's not such a great plan, and then we have to try something else, but at least that seems promising, right? So if I see something like square root of a squared minus x squared, I'm thinking x equals a sine theta, and I'm thinking of this triangle. If I see something like square root of a squared plus x squared, Here I want to put something in for x. Then when I have something like 1 plus x squared, I can simplify that down to something squared and take the square root. In this case, x equals a times tan theta. Right. Because 1 plus tan squared is secant squared. And here I'm thinking of tan theta. Let me write it off to the side. Is x over a. And tangent is opposite over adjacent. So I see that a squared plus a squared tan squared theta is going to end up giving me a 1 plus tan squared, which is secant squared. Square root of that is just secant theta. That'll let me get all of this out from under that square root. And then I just have to deal with the trig integral, which, you know, again, is not trivial, right? These aren't trivial to figure out, especially if they have secants or tangents or nasty things in them. So trig integrals aren't, you know, trivial to figure out, but at least I've maybe taken a step in the right direction. Maybe I've made it a little bit simpler. Okay. So let's look at this example. Find the area of this ellipse. X squared over a squared plus y squared over b squared equals 1. So here, when x is plus or minus a, y has to be 0, because I have 1 plus non-negative equals 1, so y has to be 0. When x is plus or minus a, and similarly when y is b or minus b, there's, in a sense, no room left for the x squared over a squared term to be anything but x equals 0. So I have my ellipse, and this is the area that I want to find. I note that I've actually got a lot of symmetry here, so I might just take, say, the first quadrant, find its area, and then multiply by 4. Okay, so let me look at that first quadrant. If I just kind of focus in here, this is where x and y are positive, or at least non-negative. So I can figure out the formula for this curve explicitly. So I'm on the positive y side, so I take the positive square root. So I have what? B times the square root. We'll take a and b to be positive. So y is going to be b times the square root of 1 minus x squared over a squared. Let me factor a 1 over a squared out of the radical. That gives me a b over a. Times the square root of a squared minus x squared. Right, I do a squared over a squared for the 1, and then the a squared in the denominator comes through the radical hits the square, and that comes through as an a. So I'm going to integrate from x equals 0 to x equals a of this thing dx. Now, what do I want to do here? I see this pattern, root a squared minus x squared. And I saw what worked for that before was using x equals a sine theta. As an aside, if you wanted to use x equals a times cosine theta, that would work too. You just have kind of some extra negatives to deal with. nothing, inherently wrong with choosing cosine instead of sine. It's just that then dx has a negative, and it's just easy to mess up that negative. So we use the sine option. So we're going to come over here, x equals a times sine of theta. And then dx is a times cos theta d theta. And we need root a squared minus x squared. And we actually already did this calculation. We saw that this was a cos of theta. So I got my 4, I got my b over a factor pulled out. I have a times cos theta from the square root. Very importantly, I have my dx, which gives me another a cos theta d theta. And here, again, I have to be really careful. Something like integration by parts, I'm not actually doing a substitution, so I don't actually need to change my bounds of integration. But here I'm actually substituting. I'm going from one variable, the x's, into another variable, theta. I need to either do my integrand, switch back, and then evaluate on x, or I need to change my bounds of integration. Here, I think I'll change my bounds of integration. So when x equals 0, that means that a times sine theta is 0, which means sine theta is 0. We can clearly see that we're dealing with thetas between 0 and 90 degrees, or 0 and pi over 2 here. Sine theta is 0 on that interval, means that theta is 0. So x equals 0 corresponds to theta equals 0. Just a lot of bookkeeping, right? A lot of little details that we have to just make sure.
Can you please repeat, like, why are we multiplying it by 4?
Oh, that was back here. Because the region that we're interested in finding the area of is symmetric. There's just 4 copies of that same region. There's the first quadrant region, but also the same area in the second, third, and fourth quadrants.
Yes, but we basically rearranged x square upon a square equation. So like why are we like x square upon a square plus y square upon v square equals to 1 belongs to whole eclipse, not just first quadrant. So why are we taking only one quadrant from that side and multiplying it by 4?
Because of the symmetry. So the first quadrant is up here, right?
Yes.
And that same area is in the second, third, and fourth quadrant as well. So we have 4 times that first quadrant area is the whole area of the eclipse, or of the ellipse.
Okay.
Yeah, we're really taking advantage of the rotational symmetry of the ellipse. Yeah. So when x equals 0, that corresponds to theta equals 0. X equals a, that's when sine theta equals 1. On 0 to pi over 2, that corresponds to theta equals pi over 2. And here I'll pull out the a squared for ab. Integral 0 to pi over 2 cos squared theta d theta. I'm going to copy this from above because we're running a little short on time. This was what that'll integrate to. I need to remember this over 2 as well. So 1/2 times theta plus 1/2 sine of 2 theta. I'm not going to put the plus c here. I just need an antiderivative. And this is going to be evaluated from theta equals 0 to pi over 2. I'm not moving back into the x world because I've changed my bounds of integration over to correspond to theta. So this gives me 2ab times pi over 2, and then minus 0. These are the bits that come from the theta, plus 1/2 times sine of 2 pi over 2 is sine of pi, minus sine of 2 times 0. Oops, sine of 0. Sine of pi is 0, sine of 0 is 0. I keep wanting to turn my zeros into thetas. This is 0. The only bit that survives is the pi over 2. Pi over 2 times 2ab gives me pi ab. So my claim is that the area of the ellipse is pi ab. And let me, in the last minute or so here, ask myself 2 questions. The first is, are the units correct? In other words, if I was measuring things in, say, inches or centimeters, are the units correct? Well, A would be in inches, B would be in inches. I'd have square inches or square units of length, which is what I expect for an area. So that's a thumbs up. My units do check out. I have a bit of an application problem here. Often in those problems, you can check units just as an extra check. The second thing that I realize is that, well, an ellipse, if A equals B, is just a circle. If I set A equal to B, then my area is just pi A squared for a circle with radius A. That does mesh with this special case. I know what the area should be in a special case of the problem that I did. I checked that special case and it does correspond with what I already know. So it seems pretty reasonable that, and let me just circle the actual answer again in red because I drew a bunch of other stuff. It does seem reasonable that the area of the ellipse that we calculated as pi AB, that is the correct answer. Are there any questions on any of this?
No.
Okay.